Today's topic is Wheatstone Bridge. Now, it is also called as a derivation of the balancing condition of Wheatstone Bridge. So, it is actually an application of very important application of Kirchhoff's laws. So, it's also simply called as application of Kirchhoff's laws to the Wheatstone Bridge. Now, what is a bridge here? Wheatstone is the name of a scientist. Bridge is nothing but a network or a mesh or a group of resistors connected together. So to form something like a closed circuit, that network or resistors itself is called as, or that group of resistors itself is simply called as a Wheatstone bridge. So in simple words, actual definition will be coming immediately here in the topic itself. Now this is a very important essay question. So essay question will be around 4 marks. Many boards, some boards even have the essay question carrying 8 marks also. So this is very important essay question, which is really an application of Kirchhoff's laws itself. Both the laws are actually applied here. So very useful. Practically, it's very useful. Its main use is to find out using this arrangement of resistors called as Wheatstone bridge. It is possible to find out any unknown resistance. Any unknown resistance, whether it is 15 ohms or 20 ohms, that value exactly can be determined using Wheatstone bridge. That's the main purpose of a Wheatstone bridge. Not only an unknown resistance, it can also be used to determine, to compare two resistances. That means two resistances P and Q are there, their ratio can be determined. That ratio, if it is known, they are said to be compared. So P is to Q is 1 is to 2 means that one resistance is, second resistance is 1 is to 2 ratio, two resistance are there means second resistance is twice bigger than the first resistance. That way, two resistances, two values are said to be compared if their ratio is clearly known. So for that purpose also, Wheatstone bridge is very useful. So it's very simple application of Kirchhoff's laws. So what is the description or construction of the, what does the Wheatstone bridge really consist of? Now here Wheatstone bridge really consists of four resistances. They are denoted as P, Q, R and S. So it can be shown like this. I'm just drawing it. Very simple diagram also. So this is the first resistance, P. And all these four resistances are joined end to end this way to form a closed circuit. Actually it should form a closed circuit. So first resistance is P, so second resistance is Q, and third resistance, actually it's shown here, I'm drawing it here, R. So see here, they are connected end to end such that they should form a closed circuit, a complete closed loop, like almost like a square loop. It will almost looks like a square loop this way, almost like a kite which will fly. So this way. So R, P, Q, R and S. So just see the order. Top left and right are P and Q. Again, bottom left and right resistance are R and S. So they're not in cyclic order. P, Q, S are cyclic order means. So this closed circuit that is formed is denoted as A, B, C, D. Simply denoted as A, B, C, D. Now here at this junction, two resistors are actually meeting here. They're actually connected here to at the junction B. So between the junctions, top and bottom junctions, B and D, a galvanometer is connected, whose resistance is capital G. This way. And between the other two junctions, so left and right junctions, top and bottom junctions, a galvanometer of resistance G is connected. So what is the purpose of a galvanometer? A galvanometer is a device using which it is possible to detect electric current. Any electric current is flowing or not between the points B and D when a wire is connected, that can be actually detected using the galvanometer. In which direction it's flowing, whether it's flowing towards downwards or upwards, also can be determined. Now galvanometer also can be used to measure electric current. It can also be used to measure electric, and later in the next topics this will be actually coming. So that is actually between the top and bottom junctions B and D. Now between the left and right junctions, a battery is connected. A simple battery or a cell is connected this way. So this is the positive terminal of the cell, this is the negative terminal of the cell. What is the symbol for EMF of the cell? A curved capital E is the symbol for the EMF. So this is the thing. Even a plug key also can be arranged here, a plug key. So by closing this plug key, it's just almost like a wire, it's actually like a metal strip. When it's pressed down, the circuit gets closed and current can flow. So this battery of any EMF is actually connected between the left and right junctions. This itself, this network or this group of resistors connected this way, P, Q, R and S, so as to form a closed circuit A, B, C, D, A, closed circuit. So we're starting with A and again coming back to A, and consisting of a galvanometer and a battery E connected this way itself is called as a Wheatstone bridge. So that's the simple meaning of the Wheatstone bridge. Now, how Kirchhoff's laws are applied here, and what is the meaning of balancing condition? Now, this is actually obtained using the Kirchhoff's laws. Now, once the key is closed, immediately the battery sends a current. So, always current sent by a battery into any group of resistors, always it flows from the positive terminal to the negative terminal. This positive terminal will be starting. So, the current sent by the battery, call it as I. It is denoted as simply I. It goes into the network of resistances, so divides into different parts here, and finally it comes out of the end C. So into the junction A it's flowing, and again from the out of the junction C it will be coming out. So this same current will be coming out. Now why the current is same in this part here? A to E and E to C. This entire part, it's single loop, single circuit, single conductor. It's a single path is available. So single path is available means various components, whether the plug key or the EMF or this conductor connecting wire. It's only a simple conducting wire are set to be connected in series. Series means always current will be the same. So in this entire single path, current is exactly the same. Now consider a current that is entering into the junction A. So here it divides or branches off into two parts. So the first part of the current flows through the resistor P. So this current is known as I1, and the second part is actually flowing into the resistor R. So this current is known as I2, I1, I2. Now again I1, once it reaches B, it again divides or branches off into two parts. So one part actually flows through the resistor Q. So I1, I2 already over. So this is denoted as I3. And the current through galvanometer is very important current. It is known as IJ. Actually, it will not be coming into the any of the equations. Even all the currents will never be coming. Only the resistances will be coming in the balancing condition, P, Q, R and S. But very important role is played by the galvanometer. So that only actually gives the name balancing condition. So what is the importance of the current in the galvanometer? Now, current in the galvanometer, immediately in the next step it will be coming. So the current in the galvanometer actually, which is actually the current flowing through the galvanometer this way, it comes towards the junction D. So now I2 through R and IG through galvanometer G, they combine here and flow out. They'll be, both of them will be combining here. So, and they'll be flowing as a single current through S. So this is the fourth current apart from the galvanometer. So I1, I2, I3, and this is simply called as I4 this way. So the current through the shunt, the current through the fourth resistance S is denoted as I4 here. So now again observe here, at the junction C, I3 and I4 they are combining, and they are flowing as what? Already we have seen this. This is nothing but the actual current sent by the battery. So this is how the currents are actually getting divided. So everything here is very simple. Now the important thing is here. Now firstly consider the Kirchhoff's current law. Using Kirchhoff's current law, easily the relation between the different currents can be obtained. Now here the important currents are I1, I2, I3, I4, and also very important current is the galvanometer current. Now firstly applying Kirchhoff's current law at the junction B. So then junction B, three currents are present actually, I1, IG and I3. I is actually not considered in the derivation at all. I is never considered. Only thing is resistances are important here in the balancing condition. Already I said 4 resistances are there. So related to all these 4 resistance, which are the currents? I1, I2, I3, I4. And along with the 4 resistance, one more resistance is there, galvanometer resistance. It denoted as capital G. Even that current also is important. Now consider only the junctions involving these 4 currents in the 4 resistors and the fifth current, galvanometer current in the fifth resistance G. So for that, consider only the junction B. In the junction B, if you're taking junction A, I is actually involved. So that's actually not related to the, not exactly directly related to the resistances. It mainly depends upon the EMF of the cell. So related to the four resistance, only four currents are there, and the fifth resistance, the galvanometer current is there. Only those junctions, that means the top junction B is the junction involving the currents I1, I3 and Ig, and the bottom junction D is actually involving I2, Ig and I4. So considering only these two junctions and applying the Kirchhoff's current law. So now firstly, so whatever things we are seeing here are simple, nowhere any complication is there. So applying Kirchhoff's current law. So whatever things, so just a moment please, I'll do one thing. So applying, and I'll write the next step here on the right hand side of the page. So diagram is clearly visible. This part is actually sufficient. Or else I'll do one thing. So diagram, I'll just move it a little upwards so that next page also the diagram will be clearly visible. Just moving it a little upwards, and so this way now this will be visible. Now you see almost visible. Almost the entire diagram is visible. So entire diagram, it's better to have an idea. Only half diagram, concentrating only on the half diagram, it will not be much. It's not be good actually. Much clear understanding will not be possible. So now applying the Kirchhoff's current law. So KCL. So at which junction? Firstly considering the junction B. So at B. So at B. So Kirchhoff's current law simply states that the sum of the currents entering a junction, or the total current entering the junction, is equal to total current or sum of the currents leaving the junction. How many currents are leaving the junction? Two currents, I3 and Ig. That is, the total current is nothing but, or sum of the currents leaving the junction is I3 plus Ig. And what is the total current or sum of the currents entering the junction? There is only one current entering the junction. So the total current or sum of the currents, or which simply means total current entering the junction, is only I1. So sum of the currents or total current entering the junction is what? Junction B. It is only single current I1. That is equal to total current or sum of the currents leaving the junction. That is I3 plus Ig. I1 is equal to I3 plus Ig. So this is a very simple first equation. Very simple equation. Directly applying Kirchhoff's current law. Applying Kirchhoff's current law, we got this equation. Next, one more junction. Junction D, involving the necessary currents related to the resistors. So at the junction D, so two currents are entering the junction, Ig and I2. So sum of the currents entering the junction, I2 plus Ig, is equal to total current or sum of the currents leaving the junction. So firstly, sum of the currents entering the junction D is what? I2 plus Ig. So at a junction D, sum of the currents entering the junction is I2 plus Ig is equal to sum of the currents leaving the junction or total current leaving the junction. What is the total current or sum of the currents leaving the junction? Only single current. Total current is what? I4. So is equal to I4. So this is the second equation. So that's how we have applied the Kirchhoff's current law at the two junctions. So next, applying the Kirchhoff's voltage law. Now, voltage law really involves, voltage law is what? Kirchhoff's voltage law already we have seen. Considering any closed circuit, for example, here we have a full big circuit A, B, C, D. That is one closed circuit. Similarly, A, B, C, E, A. That's also another closed circuit. Even small circuits also are there. This triangular circuit, you see, A, B, D, or A, B, D, A, a complete closed circuit, A, B, D, A. And next, another small closed circuit, B, C, D, B. Now, these small circuits are what? That are really important here. Because already I said balancing condition is some condition which is actually mainly related to the resistors. Why it's only related to the resistors? The reason can be understood in the derivation itself. In the next few steps, 2 or 3 steps, it can be understood. So balancing condition which really involves the resistors. So where are these resistors P, Q, R and S, 4 resistors present? In this complete circuit ABCD, or in the two small circuits ABDA and BCDB. So here what is done is Kirchhoff's voltage law is separately applied to each small circuit. Then we can get first small left triangular circuit ABDA and right triangular circuit BCDB. We'll get two equations. And from the two equations, clearly what is the meaning of balancing condition can be clearly understood. What is the importance of the balancing condition also can be understood almost from that only, from this particular step only. So next, so already we have applied Kirchhoff's current law. So next, I'm not writing the full details, you see. Actually, the running notes will be coming here. Whatever I'm explaining, whatever things we are seeing here related to the circuit, they have to be explained here. Only the mathematical steps I am writing. So later they can be written clearly, because it carries an essay question carrying 8 marks means little explanation also should be given. But entire essay question carrying 8 marks, actually only 5 marks. Even if whatever board exam you are actually going to write, if it is 5 marks also, 5 marks means just 3 or 4 steps are sufficient. The diagram itself is equivalent to 1 or 2 steps. Another 2 or 3 steps, full 5 steps are completed, 5 marks, that's sufficient. So as less explanation as possible must be written here. So even it's 8 marks, some board exams carry 8 marks. Essay questions will be carrying about 8 marks. Previously, long back, 10, 20 years like that, they used to even carry 10 marks also. For example, when you go to higher classes, there they used to carry even 16 marks, 18 marks also each question. Some entrance examinations also, previously they used to carry almost 10 marks or 15 marks each question. It's almost like a comprehension, and 4 sub-bits are actually given. A comprehension, like a paragraph is given, problematic numerical paragraph, and then 3 or 4 problems are given based on that. So totally they used to carry 16 marks. So now everything is actually adjusted. So nowhere each question carries or no board exam each question carries that many marks, 16 marks or 18 marks. Maximum they carry only 8 marks. And many board exams carry only maximum of 5 marks. So 8 marks also, 5 marks actual topic will be there unless it's too big. If it's too big, there are some very big questions, very big topics, then they carry full 8 marks, but very few will be there each year, whether you are in the 11th class or in the 12th class. Once very few such questions will be there, topics fully carrying 8 marks. So most of the essay questions they carry in the 8 marks. Only the real essay question carries 5 marks. Remaining 3 marks will be a small problem or another small subtopic. So Wheatstone Bridge mostly carries only 5 marks in the 8 marks also. The remaining 3 marks will be based related to a problem based on the same topic or some related topic related to Kirchhoff's laws or even Wheatstone Bridge or the next topic. Next topic is also somewhat similar to Wheatstone Bridge. So now applying Kirchhoff's voltage law. So now applying Kirchhoff's voltage law. So very simple way of writing Kirchhoff's voltage law is what? KVL. So applying Kirchhoff's law for one closed loop. So the closed loop here is ABDA. So for the closed loop ABDA. So the direction is clearly visible. So ABDA means we have to start at A, we have to go around the circuit completely once and come back to A. So according to Kirchhoff's voltage law, in this complete traveling of the closed loop, the algebraic sum of all the, what is Kirchhoff's voltage law? It's very simple. Sum of all the potential differences is simply equal to 0. That's the main statement of the Kirchhoff's voltage law. So applying that here, how many potential differences are there here in this closed loop? First is there is a potential difference, current into resistance. I1 into P is the potential difference across the first resistance P, which is actually connected between A and D. Next, between B and D, another resistance G is connected in the form of galvanometer. Galvanometer, it's a small measuring instrument. It consists mainly of a coil, a resistance, a conducting coil will be there. That coil will be having a resistance. That resistance is denoted as G, simply called as galvanometer resistance. So current into resistance, Ig into G, Ig into G. Current into resistance always gives what? Potential difference from Ohm's law. So that's the potential difference across BD. And next, between D and A, the potential difference also we can find out using Ohm's law, current into resistance, I2 into R. So there are only 3 potential differences, or potential difference is also called as change in potential. The sum of all the potential differences, sigma V, is equal to 0 in any closed loop. So we are starting at A. So actually direction also is important. So in which direction we are going? In the clockwise direction. That can be shown in the diagram itself, but not necessary. Because loop ABDA means the diagram is clearly in which we are applying the Kirchhoff's law. Kirchhoff's voltage law is clearly visible here in the diagram. It can be clearly seen in the, understood easily. So that's why I'm not drawing the direction of in which we are going. Actually, two directions are possible in which you have to go around the circuit once, either clockwise or anti-clockwise. Now we are going clockwise. If a diagram is shown, the too many things shown in the diagram will make it a very congested. Diagram becomes very congested. So as less things as possible must be shown in the diagram in the board exam. Very, very important. As simple as possible, the answer must be written in the board exam. So for the loop ABDA, so firstly we are going across AB. So in the direction of current, already we have seen that potential difference is, or change in potential is negative, we have seen. Why? The reason is in the direction of current always flows from higher to lower potential. This higher potential and this is the lower potential. So when we are going in this direction, we are going from higher to lower. So final potential is lower. So change in potential or potential difference is what? Potential difference or change in potential is what? Final minus initial potential. So finally we are reaching the lower potential. So lower minus higher is what? Negative. So that's the first potential difference we are getting is negative. So minus, what is the exact value of potential difference from Ohm's law? Current into resistance, I1 into P. So next we started at A and we reached B. Next from B to D, again in the direction of current we are going. In the direction of current always we are getting what? Potential difference is negative. So minus Ig into G. So minus Ig into G. See how easy the steps are. Once we are applying Kirchhoff's voltage law or the current law, the equations are obtained very easily. So from B to D we have gone. So the change in potential or potential difference is what? Minus IgG. So next from D to A we are going. Now we are going opposite direction of current. That means from lower to higher. So change in potential will be what? Higher minus lower. Final minus initial. That means higher minus lower. So higher minus lower is positive. So change in potential from D to A is positive. So plus. And what is the change in potential across the resistance R from D to A? Current into resistance from Ohm's law. Current I2 into R. So plus I2 R. So this is the algebraic sum of all the PDs, which is nothing but Kirchhoff's voltage law. The best way to remember Kirchhoff's voltage law is sigma V is equal to 0. Or it can also be written sigma PD, sum of all the potential differences. Sigma PDs is equal to 0. That way also it can be written. So these are sum of all the potential differences in the closed loop ABDA. So that is equal to 0. So this is the equation 3. So next, again applying Kirchhoff's voltage law for the loop. Next loop is what? BCDB. So in this BCDB again, all the resistances involved in this particular apparatus will be actually present. So for the loop BCDB, so for the loop closed loop BCDB. So algebraic sum of all the PDs. So BCDB. So direction itself is clear in the naming of the loop itself. We have named the loop as BCDB. So I'll just write this more clearly. B is not very clear. So for the closed loop BCDB, so we are starting at B, going along the loop this way, B to C, C to D, and D to B again, back to B again. So first we are going from B to C. So in the direction of current, the potential difference or change in potential is what? I3 into Q. It's negative. In the direction of current, it's negative. So minus I3 into Q. So next from C to D, opposite direction of current we are going. Opposite direction of current means the change in potential, just now you have seen it is positive. So it is plus I4S. So we are not directly blindly saying that blindly should not be followed. Everything is based on understanding. So potential difference or change in potential is not what? Final minus initial. And we have seen that in this loop itself, previous loop itself, we have seen that opposite direction of current when we are going, the change in potential is positive. It's plus I to R. The same way again here we are going. So any doubt is, no doubt actually you have to be remembering this compulsorily. In the direction of current, change in potential will be negative. Opposite direction of current, change in potential is, or potential difference is positive. What is the reason for that? Any doubt comes immediately, you have to check it, cross check it by using the simple meaning of change in potential is final minus initial, where it's higher minus lower or lower minus higher. We'll be getting the sign very simply, very simple manner. So next, from C to D we are going. So opposite direction of current, change in potential is positive, plus I4S, current into resistance from Ohm's law, potential difference. Next from D to B, again opposite direction of current, so change in potential will be positive again. So plus, and what is the change in potential or potential difference from Ohm's law? Current into resistance, Ig into G. So plus Ig into G. So this is the algebraic sum of all the PDs or potential differences or changes in potential in this closed loop BCDB. That should be equal to what? 0. So this is the next equation, equation number 4. So thus we got the 4 equations. Now very important thing is the galvanometer current here. So these 4 equations are very helpful. Now the 4 equations are actually Ig term is there. Now this Ig term is very important. Now one very important thing about the galvanometer current is, now always current through any resistor. Now galvanometer is also a resistor. Current through any resistor mainly depends upon that resistance value and also the potential difference across the ends of the resistor. Now across the ends of the B is the top end of the galvanometer, because the top end is connected to the galvanometer, and D is the bottom end of the galvanometer resistance. So treating this as one single resistance. Actually, this is a connecting wire. Connecting wire always is always made up of copper. The resistance is practically zero. So total resistance will be galvanometer resistance plus the connecting wire resistance 0 plus 0. G plus 0 plus 0 is what? G only. So this entire thing we can treat it as a single resistor G only, like galvanometer resistance. So now the galvanometer current mainly depends upon the potential difference VBD or potential difference across the BD, that is across the two ends B and D. Now this potential difference VBD, supposing current, we are just imagining that current is actually flowing downwards. This is possible only when potential at B is greater than potential at D. Supposing potential at D is greater than potential at B, current actually galvanometer current will be upwards. But it doesn't matter. The reason is, the very important thing is the galvanometer current should be made zero. If the galvanometer current is made zero, then the Wheatstone bridge is said to be balanced. So Ig completely disappears in all the four equations. The four equations will become even more simpler, much more simpler, because one term vanishes in each equation. Ig term will be vanishing even here also, the third and fourth also. Then the Wheatstone bridge is said to be really balanced. So what is the condition to balance the Wheatstone bridge to make the current Ig zero? That is what is the aim of the derivation. Now it can be clearly seen what is the aim of the derivation. When is the Wheatstone bridge balanced? That means when is the galvanometer current becomes, when does the galvanometer current becomes really zero? That entirely depends on the resistances P, Q, R and S. How it depends on the resistances P, Q and R and S. Now this can be understood in a very simple manner this way. Now just consider here, imagine that the galvanometer is absent here. Imagine that the galvanometer is removed. That means this current I1 directly goes to B, and there is no galvanometer. Directly I1 will be coming and flowing through Q as well. Then I1 and I3 will be one and the same when there is galvanometer current is not existing here. That means galvanometer is not existing here. The same way, this current also through the resistance R directly flows into S. There will not be any I4. I2 only will be flowing. That means I2 and I4 will be one and the same. Now the important thing is every point in electric field. Now the battery establishes an electric field in the entire network of these resistances. So because of this electric field only, always electric field is directed away from the positive charge body and towards the negative charge body. So positive terminal behaves exactly like a positive charge conductor, like a positive charge body, or really it's each terminal is actually a metal plate. The two terminals of a battery are really metal plates actually. So they are conductors. They are conducting plates. So this is like a positive charge body, and the negative terminal is like a negative charge body. So electric field will be directed away from the positive terminal, and it will be present in the entire circuit, and in near the negative terminal, electric field will be really directed towards the negative terminal. That's how the electric field is really present. Now in an electric field, at every point there is an electric potential. Always we have seen that potential is a point function. At different points, potential can be different, but potential is set to a point function. At different points in electric field, potential can have different values. And the potential difference between 2 points, how it is defined, we have seen the definition of potential difference. Always definitions of physical quantities or definitions of different properties in science and technology, they are the most powerful things. So most powerful things in science and technology or science and engineering are the scientific definitions, and almost equally powerful are the fundamental laws. Fundamental laws all will be only few fundamental laws exist in science and technology. But definition, every lesson will be having at least 3 to 4 definitions. Maybe one law or one and a half laws will be used in each lesson, not more than that. So definitions and laws, either fundamental laws or the main laws related to that particular lesson. For example, Kirchhoff's laws are the main laws related to Kirchhoff's first law and second law. They are the main laws related to this particular lesson, current electricity. But they are not the fundamental laws. Fundamental laws are the main laws from which the other laws are actually derived. So, what are the fundamental laws on which the Kirchhoff's first law and second law based upon? The law of conservation of charge and law of conservation. Fundamental laws are only few fundamental laws are there throughout the universe. That is, every phenomenon in the universe is said to be explained only using 3 fundamental laws. The first fundamental law is a set of 3 laws, the Newton's laws of motion. Second fundamental law is the set of conservation laws, conservation of mass, energy, and charge. Not the other fundamental laws. For example, not the other conservation. For example, conservation of momentum is also there, but they are not really fundamental laws. Conservation of momentum is a direct consequence of Newton's second law, and to some extent Newton's third law also. So that's not a fundamental law. Conservation of mass, energy, and charge are the fundamental laws. That's the second group of fundamental laws. First group is Newton's laws. Second fundamental law or set of fundamental laws is the conservation. Third is a very simple law, single law, Einstein's mass energy equivalence principle. So entire universe is said to be based on these three fundamental laws. All the other laws are actually derived from these laws. So whatever things so we are seeing here are simple, nowhere any complication is there. So now potential at any point in electric field in a given situation or in a given network, it's a fixed point. So potential difference between 2 points is the work done in driving a unit post charge from one point to the other point. For example, so what is the potential difference between A and B? It's the work done in driving a unit post charge from A to B. But this is found to be independent of the path. It depends only on the initial and final position. So we can move the unit post charge from A to B here, or the thing is initial position should be A, final position should be B. The total work done is called as potential difference. Or we can move the unit post charge from A to B to some other path like this. We can start at A, go to D, and come back to B again. Then also work done will be coming exactly same. The reason is the work done, the conservative field, the electric field is a conservative field. So work done is independent of the path taken. It depends only on the initial and final position. And that work done is defined as potential difference. So potential difference between 2 points is fixed. So whatever things we are seeing here are simple. So nowhere any complication is there. So potential at a given point is fixed. So potential at A is, say, call it as VA. Potential at C is VC. They are fixed points. So now potential at A, because it's near the positive terminal, it will be at higher potential. So it can be taken as a positive potential. C is directly connected to the negative terminal. Negative terminal means its potential will be negative. So C is at negative potential. So this is A is higher potential, C is lower potential. So I'll take this as say 100 units higher potential. Lower potential really it's negative. So it's better to take it as minus 100 units. But for convenience, the lower potential, I'll take it as 0. So for the sake of understanding. So these 100 volts, 100 units of potential, and this is 0 volts or 0 units of potential. So from 100 volts, now current always flows from higher to lower potential. So this way current is flowing. Now in an electric field, in the direction of electric field, potentials will decrease. So these 100 volts, VA is higher, VC is lower. So these 100 volts and this 0 volts. So from 100 to 0, gradually potentials will decrease. So somewhere here 100 to 0 means somewhere here it will be 50, and still we are coming closer and closer in the direction of electric field. Further it decreases 50, 40, 30, like that it will decrease, and finally we are reaching 0. So only for convenience I have taken the numbers 100 and 0. This is higher potential we know clearly because it's connected to the positive terminal, and this lower potential because it's connected to the negative terminal. So strictly speaking, it's better to take it as minus 100, doesn't matter. So minus 100 means this plus 100, this minus 100 means somewhere here it will be middle will be, it can be taken as 0 volts. That way also it can be taken. But this higher, this lower, easy numbers, negative numbers are always complicated unless they are must. It's better to avoid negative numbers. Certain situations, negative numbers are a must. Without negative numbers, it becomes very difficult to understand. So, very short manner, in a simple manner, negative numbers make understanding easy in many situations. So, in such situations, only it's better to follow the negative number. So, using only positive number, this 100 volt, this 0 volt. So, somewhere here it is 50 volts. It will be like that. Potential will be decreasing. Now, again, see, we have gone along this path. Now we can go from A to C even from along this path. So this is 100, this is 0. Now as we are going this way, current is flowing from higher to lower potential. Now we're still imagining that galvanometer is absent here. So 100, 90, 80 like that it will be going, and finally we will be reaching 0 volts. Now here, whatever be the potential at B, whatever be the potential, so we are taking 50 volts, say, there will be definitely another point here where the potential will be again exactly 50 volts, same as B. That means there exists along this path ADC, there exists a definite point whose potential can be same as B, because there is no other way. Along ABC path, imagining the galvanometer is absent, potentials decrease gradually from 100 to 0. Along this path also same thing is happening. That means for every point B, there is a similar point D having the same potential. Supposing the galvanometer lower end is actually connected to that point D such that potential at B and D are equal, then potential difference VB and VD, VB minus VD will be what? 0. Potential difference 0 means current will be 0. That way. So then the bridge is said to be, Wheatstone bridge is said to be balanced. So such a point easily can be determined. To that point only we have to connect the galvanometer. Imagine that we are connecting the galvanometer. then the galvanometer will be balanced. So now the important thing is the potential difference between B and D mainly depends on what? It mainly depends on the resistances P and R. So even by changing a single resistance, supposing if we increase the resistance P without changing the other resistances, automatically potential B, what happens is it will be getting altered. It will be getting altered because resistance increases means what happens here? Resistance increases. For example, Q we are decreasing and P we are increasing. Then resistance, so the total resistance, imagine that P plus Q we are not changing, but P we are increasing and Q we are decreasing. Then what happens? Total resistance is not changing means this current I1, so I3 we are just taking it to be equal to I1 because galvanometer is absent. Automatically the current will not be changing. But when P we are increasing and Q we are decreasing by some simple method, then what happens is potential difference I1P also will be increasing when P we are increasing. I1P increases means potential difference is increasing means what is happening? B is at actually lower potential. So this potential difference I1P is more means automatically it simply means that B is at a lower potential. Just think of this. It's not complicated. I'll not explain it again. You yourself can think and find it out. So if P is increased without changing Q, then what happens? B will become potential, it's still lower potential. Earlier it was 50 means it will become, so this is 100, 50, this will become even lesser, 40, 30 like that. If you are going on decreasing Q and going on increasing P. That way, just by changing one resistance, not we need not increase, actually we need not actually really change Q. Even by changing single resistance also the potential at B can be altered. So this way the potential at B and D very easily they can be altered even by changing a single resistance in the circuit. Even by changing a single resistance in the circuit. So this way one resistance or more, one or even more than one of these four resistances are adjusted in such a way that finally potentials at B and D are adjusted to be equal. Then the galvanometer current potential difference, when potentials at B and D are becoming equal, potential difference becomes zero. Immediately galvanometer will show zero deflection. No current will be flowing. So current flows in the galvanometer, the pointer will be showing some deflection. More current means more deflection, the pointer will be getting deflected. So no current means current will be, the deflection in the galvanometer pointer will show zero deflection. That way the bridge can be easily balanced by just by trial and error method. The resistances can be changed. Either one resistance can be changed or even more than one resistances can be changed. Actually the best way to change, later it can be seen that the best way of changing the resistance is the bottom resistances R and S. R and S are easy to change because that's the practical form. What is the practical form of the Wheatstone bridge? It's really called as a meter bridge. It's simply called as a meter bridge. In the practical form, it can be understood. Next topic is that only. Really, R and S resistances can be easily, not only R and S, even we can change P and Q also. But in the meter bridge apparatus, R and S are very easy to change. How it is designed, meter bridge, that will also be very, very interesting, very, very simple. In the next topic, it will be coming more clearly. Now, the important thing is the bridge can be balanced. That means the potential difference VBD can be easily adjusted by changing the resistances PQ, R and S. So if that is done, then the bridge will be balanced. So bridge is balanced means automatically current in the galvanometer will become zero. Once the current in the galvanometer becomes zero, the four equations will become very, very simple. Just see here what happens to the first equation. I1 is equal to, IG becomes zero means what happens? I1 is equal to I3. And here also IG becomes zero means I2 is equal to I4. So it's easy to understand. I1 is equal to I3. We already have seen that earlier also. And IG is zero, doesn't exist. Really now earlier we imagined that the galvanometer is absent. Now really galvanometer is present, but still because the bridge is balanced, Ig becomes zero. Automatically I1 is equal to I3 will be getting, and also Ig becomes zero means I2 is equal to I4. So 1 and 2 will become very simple. I1 is equal to Ig and I2 is equal to I4. Even 3 and 4 also becomes much more simpler because second term disappears here. IgG, because Ig is becoming 0 means minus I1P plus I2R is equal to 0. And what about this equation? This also third term becomes 0. That means vanishes. We'll get minus I3Q plus I4S is equal to 0. That's how we are getting the four equations. Now I'll write these four equations in the next step. So actually there is no place here. So I'll do one thing. So the diagram is actually very useful. So I'll just copy the diagram in another page. Actually the page is over here. So I'll go to the next page. I'll copy the same diagram. is the diagram. So we got four equations. What were the four equations? Try to remember. So I'll do one thing. I'll just shift the diagram to the right side completely, to the rough column, so that lot of space will be, sufficient space will be there. Now what were the four equations? Already we got I1 is equal to I3 plus Ig. In that Ig is 0 means I1 is equal to I3 we got. I1 is equal to I3 we are getting. So this is the called as the fifth equation. Already we got four equations. Next we got the second equation, I2 plus Ig is equal to I4. Try to remember, I2 plus Ig is equal to, at junction D, I2 plus Ig is equal to I4. In that Ig is 0 means we got I2 is equal to I4. That's the next equation, I2 is equal to I4. So this is the next equation. Already four equations completed. This is the fifth equation, this is the sixth equation. Next, what about the next equation? So I'll do one thing, I'll just reduce this. Okay, if I reduce again, it will not be, it may not be completely visible. So I'll just go back to this actual derivation. Now see here, the third equation becomes what? Minus I1P minus IgG. Just observe here. So minus I1P minus IgG plus I2R is equal to 0. The third equation. Now once the bridge is balanced, Ig is 0. What happens to the equation? Minus I1P plus I2R. So minus I1P plus I2R. So but the circuit diagram is not important here. The equation only is important. Minus I1P plus I2R is equal to 0. That's what we are getting. Equation 3 is becoming that. Minus I1P plus I2R. So I will go to the next page and write that. Remember this, minus I1P plus I2R is equal to 0. So minus I1P plus I2R is equal to 0. So this is the next equation. I'm just calling it as 7. Now the importance of this equation is only P and R relation it's showing. Now take the negative term to the other side. We'll be getting I1P on the other side. I1P is equal to I2R. So I'll write it as simply I1P is equal to I2R. That's what we are getting. So this is another form of the equation 7. So this also can be called as equation 7. So this is a much more simpler form of the equation 7. So next, consider the last equation now when Ig is changed. So this equation, fourth equation, is the last equation of the four equations. Now Ig is 0 means what is happening? Minus I3Q plus I4S is equal to 0. Minus I3Q plus I4S is equal to 0. So I'll write that minus, just remember, minus I3Q plus I4S is equal to 0. So minus I3Q plus I4S is equal to 0. So this will be the eighth equation. So but simpler form of this equation can be written as what? Minus I3Q, take to the other side, will become plus I3Q. So plus I3Q, I'll write first plus I3Q is equal to I4S. So this can be called as the equation 8. So simpler form only, it's better to call as equation 7 and equation 8. Here anyhow they are simple, then don't require any modification. This way the first four equations of the Wheatstone Bridge derivation, they are becoming 1 to 4 are becoming 5, 6, 7, 8. They are much more simpler. Now just observe here, we got these simpler forms of the equation only because of one reason. Why they are coming? Only because of bridge is balanced, Ig is 0. Then only we got the simpler equations. Otherwise the equations would have been more complicated. So what is the cause of these four equations? Main cause is bridge is balanced. So whenever bridge is balanced, the relation between the resistances and currents will be very simple like this. Now this relation between the resistance, just see here, four resistance are involved here in the last two equations, 7 and 8. Now this relation can be written in a much more simpler manner. So divide these two equations, equation 7 and equation 8. So dividing equation 7 and equation 8. Now equations, dividing two equations is actually meaningless. We can divide only two numbers. So what's the meaning of dividing the two equations? Divide the left hand sides of the two equations, I1P divided by I3Q. So I1P divided by I3Q. So but what is I1P? I2R. So in place of I1P I can write I2R. And what is I3Q? It's nothing but I4S. So in place of I3Q, I'll write I4S. So this itself is called as division of two equations. So division of two equations is not completely meaningless, but division is always most powerful things in science and technology are definitions. Mathematics is also a science. It is a science of numbers. Every operation in mathematics is having an exact definition. How division is defined? Division is actually defined only for two numbers. Two numbers only can be divided. 4 divided by 2 is 2. So 10 divided by 5 is 2, like that. So this number I1P is divided with I3Q. Only such a number, such a division only is defined. What is the division of equation? It's strictly speaking, at first instance, it is meaningless, but we are getting a meaning from the actual meaning which we know, division meaning. So everything has a proof. Division of equations also has some meaning because it's actually based on the actual division of numbers. So these how two equations are divided. Left hand side of one equation divided with the left hand side of another equation, it will be equal to right hand side by right hand side. Now just see here in this simple equation, but why is this equation we are getting? Only because 7 and 8 are true. But why are 7 and 8 true? Only because the bridge is balanced. So because bridge is balanced, then only we are getting this particular equation. So in this equation, what is the importance? Just see here. See the fifth equation, I1 is equal to I3. So see here, diagram also, I1 is equal to, just see here, see the pointer. Everyone observe the cursor compulsory. So I1 is equal to, so I'll just make it a little more clear actually. So actually it's not coming in the entire page. So if I'm showing this equation, actually top equations are missing. This equation, bottom equation I'm showing. So if I'm showing the top equation, actually bottom equation is missing. So I'm just making a small adjustment so that everything is visible. Now almost everything is visible. Now see here, this is very simple. Even diagram also is visible now. Now just see here, I1 is equal to I3. So here actually this part is not visible, but I'm pronouncing it. So I1 is equal to I3. So I1 is equal to I3, we already know. When Ig is 0, I1, just observe the cursor compulsorily, I1 is equal to I3. So I1 is equal to I3 on the left hand side. Because they are equal, directly they can be cancelled here. Simply I'm just cancelling. I1 is equal to I3, they get cancelled. And what about I2 and I4? Equation 6 you see, I2 is equal to I4. Diagram also you see, I2 is equal to I4. So they also get cancelled. So why they are getting cancelled? Because they are equal. Why they are equal? Because bridge is balanced. So if the bridge is balanced, we are getting finally that P by Q is equal to R by S. So therefore we are getting what? P by Q is equal to R by S. So only because the bridge is balanced, the relation between the four resistances, we are getting it as P by Q is equal to R by S. This will never be getting if Ig is not 0. So whenever the bridge is balanced, always the four resistances will be related as P by Q is equal to R by S. This is very, very important. Now balancing of the bridge is very, very simple. We already know how to balance the bridge from the definition of potential or from the conservative nature of the electric field already we have seen. Bridge can be balanced very, very easily just by moving the lower end, lower terminal of the wire connected to the lower terminal of the galvanometer. Very easily it can be moved on the complete this lower part ADC branch, complete ADC branch. We can just move this end of the galvanometer and we can locate a point D having the same potential. That's very easy to balance. Once it is balanced, the balancing of the Wheatstone bridge practically is very, very useful. And theoretically, what is the importance? If it is balanced, the relation between the four resistances, when we are moving this way, so whatever things we are seeing here are very simple, nowhere any complication. Supposing you have any doubt, the best way of moving the wire. Now, supposing you are getting a doubt that when we are moving this end of the wire this way, so there is some point here having D having the same potential at D. How to understand that? The best way to understand is in a real practical Wheatstone bridge, this lower two resistances R and S already I said they are very easy to alter. The reason is this entire ADC branch here, ADC part of the Wheatstone bridge is actually constructed from a single resistance wire, a uniform resistance wire is taken of 1 meter length. That's why then the Wheatstone bridge is called as a meter bridge. It's called as a Wheatstone bridge in which the lower resistance R and S are formed by a single uniform resistance wire of 1 meter length. Such a Wheatstone bridge is called as meter bridge. Next topic it will be coming clearly. Now that is actually very, very important here because imagination becomes much more easier. Now we can see that it's a single uniform resistance wire. Then what happens is that in the electric field here, always between any 2 points, because it's a resistance wire. Now here this is a connecting wire, copper wire, so its resistance will be 0. But when a resistance real wire, uniform resistance wire is taken, every part will have a resistance. So every part there is a potential drop. Potential drop means potential difference exists. Because current into resistance, copper wire, it becomes complicated because potential difference will be 0 across any part of a copper wire. So with that will give some theoretical complications to understand if you are thinking or directly you got that point while thinking. It becomes very difficult to understand when we are moving the end lower end of the galvanometer connecting wire across this portion to different points, why the potential is changing, that doubt can come. It will not be changing if it's a copper wire. Supposing it's a uniform wire like 1 meter resistance wire, then at different points potential will be really, then different points potential will be differently decreasing. So it is 100 volts and this point is 0 volts, means continuously 100, 90, 80 like that uniformly it will be decreasing. Then definitely we can locate a point D having the same potential as B. That's how practically Wheatstone Bridge very easily it can be balanced. Once it is balanced, directly we can use the balancing condition which we have derived. P by Q is equal to R by S. P by Q is equal to R by S. Then using that equation, very easily many unknown things can be determined. Again, I'm just going back to the next page again. So this way, once the Wheatstone bridge is practically balanced, automatically we can get the exact relation between the four resistance as P by Q is equal to R by S. In this, supposing three resistances are known, already given. We have taken only three known resistances. The unknown resistance, say P, it can be determined. Or if two resistances are known, R and S are known, say, then unknown resistance P by Q, that ratio can be determined by substituting known R and S values. This can be understood more clearly in the next topic. So this is called as balancing condition, because only when the bridge is balanced, the relation between the four resistances will be coming this way. So this is simply called as balancing condition of the Wheatstone bridge. So derivation of the balancing condition is very, very simple. Any doubt is there related to the derivation, just think of the diagram. Very easily it can be understood. Any complicated doubt is there, always the best way to get that doubt clarified is imagine that the galvanometer is absent. Any question can be answered if the galvanometer is taken to be absent. Then the circuit becomes very simple. Without galvanometer, directly single current will flow through P and Q and another single current will be going through R and S. Very simple diagram it becomes. Any question can be asked. Then you connect the galvanometer, then whatever question you have, that also can be, whatever complication you have, that can be very easily clarified. So nowhere, so whatever things we are seeing here are simple, nowhere any complication is there. Okay, so that's the balancing condition derivation. Now very quickly within 2 minutes, now there is no big derivation, just four simple equations using the two laws we got, and then by making the bridge balanced, the four equations are becoming just very simple. They are becoming very simple form. This way they are becoming 5, 6, 7, 8. They are much more simpler than the earlier four equations 1, 2, 3, 4. Then dividing the last two equations, we are getting the balancing condition. That's all. Three main steps, we are getting the derivation fully. Now this diagram is actually not required here, so I'm just removing it so that because it's just copied from the previous page itself. Now the running note should be written. Now in this part there is not big change, so derivation will be ending here. So I'll draw a line here ending the derivation. So in the previous page, steps are very simple here, the four steps. Here little matter will be coming. That matter, how to write, I'll just explain. So immediately in the next frame itself, I'll put the matter here. Quickly take down that. So this is the actual running notes. I quickly written the running notes so to avoid, to save time actually, to avoid loss of time. So this is the ready running notes. So everything actually already I said, the equations entire derivation we already completed. So in between the derivation step, that means in between this diagram and the equations, little matter has to be written. So that's the matter here. Very simple matter. So very easy to write. So that's the thing. So you're starting here with the heading. Next left hand side, firstly you have to take this left hand side on the left hand side of this line, dividing line. So completely take up to the end. Here this is the end. Just see here. This is the end. You can just see the bar here, vertical bar here. Observe the cursor here at the right end of the screen. So this is the end. And again on the right hand side it's taken from here. The equations everything as it is. Only the matter I have written this paragraph again. So this is the complete page. And next, the next page I am showing. Put the video to pause at each point and take the running notes. Next page is starting here. So you see the bar here, vertical bar, movement bar, sliding bar, the page sliding bar. So it starts here as ig is equal to 0. So then it continues here. This is the completion. That's all. This is the complete running nodes. Quickly take down the running nodes quickly. Within a few minutes, 5 minutes, it can be completed. And then attend the next class.